We will start streaming. Okay, notebooks open. We have done three types of reactions, single replacement reactions. And this would be a good place to start. Right now, determine whether these are synthesis, single replacement, or decomposition. Just write S, R, D, or S beside them. And I will call upon you to tell me which one's which in a moment. The last one. The front page looks like that. And while you're doing that, I will start with attendance. I don't say. Let's see here. Ayana, Asha, Besma, Charlie, Wilbur, Elena O. Don't see. So you were working on this page. Of those three types you've gone on, synthesis, decomposition, or single replacement, classify them. And then we'll go through it right here. Elena Farrow. There you are. Felix. Jack is not back yet. Lilia. There. Luke. Manuel. Nika. Orion. Portia. Roman. Santiago. Savannah. Sierra. No Sierra. Sophie. Soren. And Yash. No, I don't say. Why are you so late? Okay. We were working on this page of the last notes, classifying them as synthesis, decomposition, or single replacement. So follow your notes and start with that. And just as a hint, of the three types, if you squint your eyes and look at them, synthesis should be a couple of things going to a larger thing. Decomposition would be a larger thing going to some smaller things. And single replacement should have some sort of exchange of partners. In which like replaces like. So they'll have the same number of things on both sides. Okay, first one, I'm going to say decomposition should look like one big thing going to smaller things. This is two things going to two more things. Single replacement would look better. And the fluorine, a non-metal, is replacing the chlorine, also a non-metal, so like replaces like. Sodium fluoride and chlorine gas. Next one, a later fire. Decomposition. Big thing going to smaller things. 4 smaller things, in fact. Savannah? Louder? Synthesis. Smaller things going to one big thing. Wilbur? Decomposition. Big thing going to 7 smaller things. Rowan? Synthesis. Making up to a larger thing. Yes. Single replacement. Yep. The chlorine in this case replacing the bromine, kicking it out. Luke. Single replacement again. Tin replacing the gold. Orion. Synthesis. Soren. This going to that one. Maybe. Yeah, decomposition. And Lilia. Synthesis. Any questions about this? Great, we can get on to our next type of reaction, which is double replacement reactions. there.
Silver nitrate.
Two compounds switch around and switch partners. So that's if you have then A, B plus C, D, you switch them around, but you have to switch them correctly. So switch them around correctly, put them in on the other side in the right way. You don't even have to know what elements they are. I'm just going to grab the test. Only a little bit, but hopefully this will work. What are the correct products then? BC, CD, what? CB, AD. Why would it be? It has to be CB and AD. You can put them in a different order. You can go AD and CB. But nobody's ever go CB. Why can't you switch it? What kind of element is this? The beginning. Metal. So the other side, it must still be a metal. So we'll go first or second. So the ones that are in front always have to stay in front. The ones that are behind always have to stay behind. So they just switch partners. So A can't go with C. You'll have a completely different reaction at that point. I mean, theoretically, that could happen to but in this type of reaction, A has to go to D, C has to go to B, and C has to be first because it's the metal. There's only one particular way it can go. The example I have here for you is right up this product. I've got PbNO3 2 plus Ki. Predict the products. solution, that's our lead nitrate. I've got a very slightly yellow solution, that's our potassium iodide. We add them together. That makes one particular very nice yellow compound. I think I've talked about this before, it's yellow paint. Very, very poisonous. Lead is wonderful for paint. It makes a long-lasting color. On the other hand, if you put it out in the environment and it comes out, then you've got lead poisoning. Right? Those nitrates and potassium iodide. So combine those together. What's the product? Using the same logic as from before. And I heard right away, KNO3 and PBI, and that is incorrect. Yes, I'm saying. You're on the right track. You're on the right track, yeah. The 2 goes in the eye. Reason for that, it's the lead, so you're on the right track there. It's the lead that's +2. The nitrate, if you look it up, is just -1. So we still have to figure out which one's which, +1, -1. So these ones end up being +1, -1, but this is +2, -1. So when we crisscross, we get that compound. You still have to adjust for their charges. Notice we weren't trying to balance. You don't balance until after you figure out everything about the compound. And once you've figured out what their charges are and that part's done, then you can start balancing. So balance that out as well. Yep.
You said PBI2 plus KNO3.
Oh yeah, it doesn't matter the order. It is like at a dance being somewhere else on the dance floor. Volunteer dance. The jacket type would probably be the best one. What do you have underneath that jacket? Okay, that can work. Yeah, big on the jacket though. And here, yes, because I think you're the only one that matches. Excellent, excellent. And perfect. Great scales. So red sweater with gray, and then you're at the traditional snowball dance and dancing with your partner. It turns out you have to do dance. Excellent. That is acting. And then you realize both of you realize at the same time, other person, terrible dancer. And so, and this is the important part, you have to switch partners, but if you both switch partners, you're going to end up with the same person. So switch partners correctly. There we go. And now we're dancing again. They're with the partners that are perfect. There was the arm swinging. Please give them a hand. So this is like cutting in no, not cutting in. This is switching partners. The other one was cutting in. That's single replacement. And then I think last year we had someone from Alberta, and they said, "Oh, it's like the do-si-do in a dance." Do-si-do. When you're doing country dancing. How do you know which one? You look at their original charges. The original charges never change. So if you have PbNO3 2, Now, the charge of nitrate you can look up. -1. So you go, oh, that's -1. And I have 2 of them. So this one has to be +2. And on the other side, it will also, its charge won't change. So you figure it out and then know that it doesn't change onto the other side. And so, and this one you can look up as -1. Iodine you get from your periodic table is -1. Potassium you also get from the periodic table is +1. It's an alkali metal. And so all the other ones you know. It's only that one that we required Roman numerals if you had to name it. Neutralization. This is what our entire lab is about. We can call it neutralization or acid-base reactions. H2SO4 plus NaOH goes to H2O plus Na2SO4. We have done that. All acids have H in them, especially at the beginning. Bases all have OH. And in the same vein, if one product is H2O, what is the other product? AB. Well, almost AB. In this case, generic case, no. There's something a little wrong. AB is not in the right spot. There's something a little wrong with it. BA. Because the base, if you look at the bases you had, I think you had like potassium hydroxide, calcium hydroxide. They always have a metal. So the metal always goes first. And then the acid has that non-metal ion, hydrogen chloride, sulfuric acid, H2SO4. The SO4 would be the A in this case. And so that comes out, and that acts as the non-metal, the negative side. This is an acid and a base, making water. And this product here, that's the salt. It is essentially just a weird type of double replacement reaction. Students often get that confused because they'll see, oh, look, you've got H, OH, and that essentially makes HOH. One just pops in the other. So it looks a lot like a double replacement, and technically it is. I don't know why I started right there. And then the other part, let's go there, let's go that one. We have the metal and the non-metal making the salt. Special type of double replacement. We've done an entire lab now on those, and we've learned some of their properties. So on the next pages, now I didn't have you as one of the tests eat the acids and bases. However, lemon is very, very acidic. What flavor is a lemon? Sour. Acid means sour. That's where its original name comes from. So it tastes sour. Chemically, it gives off a proton or a hydrogen ion. Also known as a proton. Because if you have a single proton on its own, a proton with an electron is hydrogen. If you take away that electron, there we go. You just have what's called a naked proton. It's got nothing else, just one single proton, hydrogen all by itself. And most atoms of any kind will have some electrons on it. Even if you take some away, there's always that last little barrier. But a hydrogen ion, you take that away, and it's just a naked proton. All that force, all that +1, is now concentrated onto a little tiny area. And that's what makes it so reactive. So most atoms, they have a charge. They have still some outer layer electrons. They're big. But you take all that space away and you just have that tiny concentration of charge. That tiny concentration of charge now can rip things apart. That's why acids can break things up. If you take a small thing and concentrate it into a very tiny area, you now have quite a lot of force.
How do you concentrate hydrogen?
That's because there's only one proton. If you have, for example, the next one down, lithium. Lithium is 2 electrons, and then it has an electron. And then you take it away, it still has that, and that area is huge. Like I did the joke where I like drew a little Bohr model, and I said the nearest electron, and then I pretended to run away like 5 football fields. The most of the atom is empty space. But now we've taken away all that empty space and concentrated that charge into one spot. I remember a dinner party my parents hosted, and they had these nice hardwood floors. And a lady didn't notice that the little tip off of her high heels had come off. And so as she was walking across the floor, she was punching in holes into the hardwood. Chunk, 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 chunk. Because it's not like you walk across the floor, you're not going to do that. But all of her mass was concentrated into this tiny little area. We also had a D8 cat. If you destroy the road when you put a D8 cat over it, the Ministry of Transportation is going to be down and get you in a lot of trouble. So we would put wooden slats on top, and my dad got tired of that, so he would just put on wide treads because he would need them anyway. And he would just go over anything. You could lighting a piece of wood, it would go or wouldn't even leave a mark on the wood because the wide treads spread the tons of mass over such a wide area. It no longer was effective, wasn't pressing into the ground. So if you change the amount of area a force is in, it can become vastly more powerful or vastly less powerful. And so one of the reasons the hydrogen ion is so reactive is that we have all of that whole +1 in a little tiny spot. What color do acids turn blue litmus? Red. It looks pink, sure. Now, we didn't specifically measure its pH. It has a pH of less than 7. And pH is just a measure of acidity. If you are greater than 7, you are a base. If you are less than 7, one of the ways you measure is with litmus. And so you know it's less than 7 if the litmus turns red. And bases turn red litmus. Then you're neutral. Then you have an equal amount of acid and base. It's neutral. Water. I have to be careful. I can't say that there's no acid or base there. They're just there in equal amounts. As you'll learn if you go on in chemistry, if you heat water up, it does become more acidic, but it also becomes more basic. You get greater amounts of both of them. And so it's still neutral, but it also becomes more corrosive.
Is that why water tastes that way? Why water tastes
If you don't have any acid or base, it doesn't have much of a flavor, yeah. And if you have pure distilled water, there's no, often what you taste are the dissolved minerals, actually.
So if you have distilled water, it tastes like that?
Pretty much, yeah. Other than it would taste cool or warm.
Yeah, it's like nothing else I've really tried.
Yes. Oh, no. pH less than 7 is acidic. Yep. So if you have a pH scale, oops. Do I have a periodic table on here? There we go. So if I have the pH, pull your periodic table. Here's 7. Here's neutral. Neutral is an equal amount of acid and base. Anything above that is basic. Anything below that is acidic. Acidic means you have more H plus than you have OH minus. And basic means you have more OH minus than you have H plus. It doesn't actually mean they're gone. Also, it jumps, and this is an artifact. We'll do this next year. Of how we do the scale. 6 is 10 times more acidic than 7, but 5 is 1,000 times more acidic. Sorry, 10 times, 100 times. 4 is 1,000 times. 3 is 10,000 times. 2 is 100,000 times. A pH of 1 is 1,000,000 times more acidic than 7. It jumps by a factor of 10 each time. So if you see, oh, it's pH of 3, that's grapes. Maybe I can eat that. 2 is only 1 less. You just jumped from 10,000 to 100,000. You jump a fair bit. Stomach acid at a pH of 1 is really, really acidic. Pardon?
What's like an example of something that's 0?
I don't know. There's some hot springs which literally have chemicals bubbling out from the earth. Also, it doesn't end here. You can have a pH of -1, and you can have pHs of 15. It keeps going. This is not an artificial scale. We didn't invent the scale and said, oh, we'll just make the middle 7. We're actually measuring the concentration of H+, but it requires a bit of knowledge from chemistry 11 to do, so we don't go into it that much. But 7 is a measurement; it's not an artifact, and so the scale goes beyond these. So the easiest thing I could do to get a 1 molar pH is to get a 1.0 molar solution of hydrochloric acid. I just make it in the lab. But a natural thing that's that acidic, I think we've had acid rainfall once or twice on our planet. It's been that acidic after smokestacks. Zero. Yeah. But I'd have to double check most of the things. Volcanoes, when they give off ash, will sometimes you'll get quite an acidic or basic rain, depending on the ash that they're giving off.
So you can make stuff that's like -10.
At some point, no, because you just can't dissolve that much acid in the water.
Yeah.
So the molarity of sulfuric acid is only, I think it's maximum 18 molar. So you can get down to, that would get you down to -1, and that's it. It's just physically impossible to put more acid in. Bases turn red litmus blue. And if you forget, base turns things blue, and acid turns them red, if you find that helpful.
What is pH? What is that in red?
Here? Greater. It gives off the hydroxide ion, as I've been drawing. And bases taste bitter. So coffee is basic, lightly, but a little basic. This is a survival mechanism. It turns out a lot of poisons are bitter. And so we've evolved to not really like it as much. You can learn to like it in the taste of coffee. But in general, if you're eating a food and it's bitter, it just might be poisonous.
What about grapefruit?
That's sour.
Why isn't it?
If it's a bit bitter, then sure. I mean, grapefruit's terrible anyway.
Yeah.
Who would eat that? Ugh. Salts, any compound that you can have can be a product. So any ionic compound ends up being a salt, because if you have, for example, NaOH plus HCl, hydrochloric acid with sodium hydroxide, that goes to NaCl. NaCl plus water. And then you get table salt. But you can take any metal. Let's get someone to give me their favorite metal. Bismuth? BiOH2. Favorite non-metal, please, Charlie? Pardon?
I don't know.
You can use polyatomics, any non-metal.
Which
Yeah, Jason. Chlorine. HCl again then. Now we've made a salt with bismuth and chlorine. What charge is on the bismuth? Bismuth? Right there. I heard +1 to minus. It's not 93.
It can go either way.
Yeah, it can go either way. So you have to look at this to figure out its charge. If it has 2 here,
Oh, yeah.
it's +2. So on this side, it's going to be Bi
Yeah.
Cl2 plus H2O. There's our salt. You can make any ionic compound. You just have to get the corresponding metal with hydroxide and the corresponding non-metal with hydrogen, make the acid and the base, and you can make any ionic compound. And so all ionic compounds are known as salts. pH equal to 7 is neutral. It's neutral in grade 10.
Oh, God. Wait, it's not basic.
Right?
It's not basic.
Salt is neutral. Water is neutral. So if you add an equal amount of acid and base, they neutralize each other. Yes. Table salt is, absolutely.
For now, it's
And most salts for now are neutral.
And is this just something I thought of with the neutral things like I know water's like good for the body, but not really make you fat, so it could be
Yeah, it's its own nutrient. It's not a calorie nutrient.
adding too much like salt.
Oh, because salt sucks. And by salt sucks, what I mean is, if you have, what's the closest thing you've probably done? Ever put a marinade or a salt over top of meat overnight? Right. So what you're doing in that case is if you have a membrane and you have water on one side and water on the other side, but you have salt on the other side, the water will move to where there's less water.
Yeah, that
So through diffusion, and so it goes to the side that's more salty. So salt sucks; it sucks things out of it. If you have too much salt, that will suck the water out of your cells. So you want the right balance of salt. If you exercise too much and you don't replenish the salt from your sweat being sweated out, you now have too little salt to run all those processes and maintain that balance in your body. You could actually get yourself into serious trouble. People who have hiked and then they're eating like granola bars and other things that don't have a lot of salt in them during multi-day hikes, often you'll bring along salt pills just to make sure that you get enough salt.
so I have a question.
Yeah.
When I it's like I don't know, my brother gave me like salt one time when I was dehydrated because I wasn't drinking enough water. Does that do anything or is that just like
If you're dehydrated,
yeah, that's what I thought too. It's just being dehydrated.
yeah, well, if you've lost salt along with the water, okay. Eating more salt might be really, really bad if you just lost a lot of water. You should now, if you drink water with the salt, that's good. You're replenishing some of it. This is what companies like Gatorade will advertise. Like you get electrolytes,
Yeah, that's what he said. He said it gives you like electrolytes.
but you need water with it.
I drink water with it.
Yeah, then you're fine. The other part is the Gatorade also gives you a ton of sugar, and it's not actually all that great. If you want to have a good electrolyte booster, just eat a banana with your water. It's less sugar. It'll give you more of the electrolytes you need. You can get something called Pedialyte, which is like Gatorade without all the sugar. Tastes terrible, but you get all the electrolytes from it too. Okay, this one. Only thing for this one is to tell if it's a neutralization or not. You don't have to identify the type of reaction, although I may ask you to. So is this an acid-base reaction or not? And then if it's not, see if you can get the type of reaction from that. And then we just have one more type of reaction. And then I should think about expanding your quiz. Expanding. No. Yeah, someone not only grabbed them, but I wanted to work on it. Bring the work on. Yeah. But it's work book. Someone grabbed all the textbooks and all the workbooks. Yeah. How do you know if it's an acid? There you go. There is the H if it's an acid. How do you know if it's a base? Oh, wait. And what does it have to make if it's an acid base? Water. And the corresponding salt you get. The metal from the base and the non-metal from the acid. Did anybody bring that one up? I know, like the soft cover one. Did you bring? Someone stole it. I'm just so pleased. That one didn't start with an H. What does that one start with an H? So they didn't want to hear the order. No. So all the criteria, you do need an acid in the base, but it also has to make the salt in the water. So that was not because it made water, but it made the salt. Also, it has an H in it, but that's not an acid, that's right. And it doesn't have an OH. So the one thing you need it has an H. Does it have a hydroxide? No. So it can't be. So for an acid base reaction, it has to fit a lot of criteria. It has to have the acid part with an H, it has to have hydroxide in the second part, and the products have to have water, and the corresponding salt. Yeah, so it has an H, got an OH, and you've got H2O, and you've got the salt. Oh, hydroxide is hydroxide is okay. If you pull up your data table, you see that? Right, there's no hydroxide, so it's not an acid. Yeah, but what type of reaction is it? There's a decomposition. Yeah. So when I say hydroxide, I literally mean there. That's it. You have to have any element. H, H, O, H. And then one.
So then this
That one can be. Right? Doesn't have two things. Well, it's got an OH.
Yeah.
So what they did is this one happened, right? Now they just flipped them. If they're, the two pairs that I have on this side, when the people were dancing, if I switch to the side of the room, I would still be nice and so the acid doesn't always have to be written first. Does that make sense? Okay. Yep. And these things. We just did acids and bases. And an acid starts with H. Their base has hydroxide. That's an acid-base reaction. It's an acid-base reaction. Yeah. That's just two names for the same reaction. Yeah. Okay. So I'll go over it now. What needs to be on both sides? So one of the things you're looking for, an acid has to have an H with something else. A base. Oh, and I should simply because I saw this enough times. Some people were coming up with the idea, and this is before I think it's somehow how I present it, that the acid always has to come first. It doesn't. You also have to have some sort of metal with a hydroxide. In this case, I'll just make it 2 just to make it look a little bit weird. So this is the base, and this is the acid. And then they will always make water. So H plus OH makes H2O. And then the metal and the non-metal here will end up, what did I do that in blue? So all of these elements have to be present. You have to get the base, you have to get the acid, it has to make water, and you have to make the salt. Nope. I mean, you have more than one there, but you would fix that in the balancing. It'll always make water. H2O2 is a very unstable compound. That's hydrogen peroxide. It won't be made naturally by this process. And so, and you don't, things are made by in terms of what they are, not by the ratio just in here. This has 2 just because 2 of them attach. It's really just H plus OH. Right? It just happens to give off 2 of them. So the first one, is it an acid-base reaction? For me, please. Asha? No. What type of reaction is it? It's a synthesis. Next one, Nika. No, why not? There's no water here. Do you know what kind of reaction it is? Or take a guess? In a way, in that you are making two things, but you don't end up with any more on either side. Think about the one, they do seem to switch partners though. So HSO4 became MgSO4, MgNO3 became HNO3. Double replacement. Esma? What's that one? Yeah, that's an acid-base reaction right there. Perfect. We have the acid right here. We have a base. The key, I spelled based. I don't, okay. It's the OH that makes that a base. It's the H that makes that an acid. We get our H2O. We have our salt. We have all the essential elements of an acid-base reaction. How about the next one? Portia. How many items do we have over here on the left? I'm not asking for the number of atoms. How many different types of compounds do we have? No, just one. I think you're trying to count atoms in some kind of way. There's only one thing. It's H2CO3. It is an acid, but is there a base on that side? I'm asking Portia. Portia? That's okay. There's an acid here. Do we see anything else there? No. There's no base there. It does make water, but this is more of a decomposition. We have one thing going to many things. There's no base. There's no other parts. Santiago, next one. Santiago's not here. There's too many left. We'll get him next time. Felix. We have the acid here, I'm presuming. Where's the base? Well, which one? Oh, what does a base need to have? It needs to have OH in it. So that'll have OH in it? No, not a base. You do get an acid on this side, but we want a salt and water on this side, so this is not an acid base. If you have two things going to make a bigger thing, what type of reaction is that? It's a synthesis, yeah. The last one, Sophie. Yeah. We have the OH that makes it a base. We have the H that makes it an acid, and they come together to make the water. We have the metal going to the metal, and the non-metal going to the non-metal, and so we have an acid and base making a saltless water. A single replacement. Okay, this is going to sound bad, but a single replacement only has a single replacement, and where a double replacement has two of them. So, to very quickly, A, B plus C, D is a double replacement, but A plus C, D is a single replacement. There's only one thing, and it will bump out one of those, whereas these will switch partners. That make sense? Okay, last reaction. Would you like 12 hours of relaxing fireplace sounds? No. That's what we just said. Because it's a combustion. I'm probably getting copyright struck right now, just so you know. Lovely. For a combustion reaction, ladies, I would like you, let's do C6H12O6 plus oxygen. Predict the products and balance. This is a combustion reaction. If you have any type of carbon, hydrogen, or carbon, hydrogen, oxygen compound, you always react it with oxygen. It always gives off water. That's similar to acid-base reactions, but it also gives off CO2. That's what a combustion is. If you take wood and you burn it, you give off water, CO2, and then what's left behind is just ash. And the reason why you get so much less afterwards is for the same reason why you get so much when a tree grows. A tree, where does a tree get its building materials from? Like, how does it become big? Not from the soil. And what is where does photosynthesis? That's where it's get its energy. Where does it get the actual cell walls, like the actual physical part of the thing? Pardon? No, it makes sugar, yeah. Not oxygen, it makes oxygen. Not water. CO2. Trees suck in CO2 and make sugar and then make their cell walls. Trees are made out of gas. It's not gas anymore, but they suck in the gas as raw material and then create the tree. When we burn the tree, we are taking that solid material and putting it back into gas. That's why we have had a problem with global warming and CO2, is that all of those organic creatures died and became oil. And our planet got used to not having that CO2 because it accumulates CO2 over time. And then we found them all and then decided to burn them all at once. Over the space of they've been lying there and they've been accumulating for millions of years. And we decided we're going to burn them in a couple hundred. Turns out you can't quite do that without having an effect in the atmosphere. And so we've kind of learned a lesson on that. But it's just, they sucked it out from the air. So, if you were to burn sugar, which is what that is, plus oxygen, what are the two products of a combustion? Yep. Ooh, you've got that memorized.
I wasn't sure if I did 6 CO2.
Yeah. And you're just missing the 6 on the O2, and that's it balanced. That's the reaction that governs pretty much all life on this planet. We take in sugar, we burn it with oxygen, we get off energy, we breathe out CO2. Trees do the opposite. Trees take in the CO2, they bring up some water, and they make sugar, and give off oxygen gas. That's photosynthesis. Pardon?
In the chemistry terms, that is.
Yeah. In the chemistry terms, that is photosynthesis. And then you can take that glucose, that sugar, and then use that to make a host of other compounds. And so when we're burning a tree, we're turning it back to the atmosphere. Part of the problem is that we've accumulated far too many of these trees in the form of oil and coal, and then we're burning them up very, very quickly. More CO2 than our planet can react. Okay. Now, I did learn that most of us did not have our booklet. There it is. Homework. Page 112 to 113 of your workbook. And let's do some practice on that. Yeah. get out. Right now, however, yep. You're wrong. So let's take identify and give the products of the following types of reactions. And I will put you in groups. Do this on the whiteboard. How many whiteboard spots do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. And how many people do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We have an odd number. So you get the end of class. I just got a few minutes. Three people per. Sure, that sound looks good. Find your people, Ayana. You can just pick a group and join them. And then find a spot at the board. Everybody have a group? Anybody still need this up? I'm going to pull it away. And I'm going to put in some other ones.
We're gonna split that. Yeah.
Predict the products and identify the type of reaction.
What is that? MG or what is that?
MG.
Is that CU or C4?
CU.
MG plus D it's like U. It'll be
You did something good.
You did it.
First, you want to make sure your compounds are right. That looks good. And the type of reaction. Excellent. Those are good products. Not all of your compounds are the right. With water. You're probably NaSO4. Oh, you have to balance. Technical looks really good, and the velocity is really good. There's one error in the first one. It's the same error everyone's made so far. It's in the NaSO4. Was a base. So acid plus a base always makes what kind of product? And it's only like a double, like there's two products always. And water. Your H2O. Those two complicated. You don't have to. Pardon? Oh, you just fix that on yourself. This is going. It just makes it easier. Like, you know, when you put the windows in front of you, you balance it. That's good. It always makes it easier. So the fact that it's H2 because that H2SO4 and give off an H2. You have to balance it. That is the concept. One of those is the salt. Now your NaSO4 needs some work. Ooh, nice. You got your NaSO4 next. Nice. That one looks good. Now identify the type of each reactions. Identify. Oh, yeah, you got that. Yeah. About the what? Yeah. Yeah, you can balance. They have balance. They've got all the right things. If you're developed, where's yours? Well, then I'll be over there. Oh, NaSO4. You got it.
I wasn't here last week. Like, if we do like any work, like a worksheet or anything, just go through like a slideshow or watch it. Yeah.
NaSO4. Another one that's really good.
I mean,
Oh, and you're saying or free. This isn't Belgium is what we're talking about. You get to get the church. And NA plus one and SO4.
Yeah.
Well, now you're trying to put more over.
Oh, no, you're
Oh, no. Your problem is that getting SO4 stuff. Yep. There's two sodiums. Because the charge has SO4. Yeah. And so the charge on the ending is +1, like I think +1. And so you need two of those. Now you get that. Once you've got the tension reactions, balance them. You rewrite that, you need an arrow, and you make that longer. And that's probably where we should go. Draw out that bottom reaction. That bottom reaction, put it out in a straight line so you can balance it. Oh, there you go. How did you get in the answer? You change it on both sides as well. You can't change it. I mean, like, there's usually armies that people want to start chopping them. So the SO4 and the SO4 now, big numbers in front. Big numbers in front. There. You're very close. Yeah, you have to. Yeah. Yeah. Perfect. It's good. Because look at the numbers here. 4, 4, 2. Would you reduce that? Why not? No, it wouldn't be. But you don't see anything there. Well, you can also change some of the numbers. This one has that you see that these are all the visual. answer.
1, 2, 2, 1. No, they're all really big. That's already done. That's already good. And that was the name. Oh, this one passed him. That's right. You know, pages, start the pages in the workbook. That was too Friday. Do you have a quiz? Quiz. Yeah, I can do that.